Welcome to SanfordFlipMath. This is AP Calculus. We are steadily working through the Finney, Demana, Kennedy book for calculus for the AP Calculus course. Just a quick reminder before we get into section 7.2, which is about area. Just a quick note. I've been having some people tell me that there are some issues with watching the FlipMath videos on phones, and can I just encourage you to try watching them in the web browser like Safari instead of watching them through the YouTube app. I'm not sure what's going on, but sometimes, and it's not every video, but sometimes the video starts off fine and then maybe 30 seconds in or whatever, it goes very fuzzy. And I'm not sure if there's just a memory issue going on there or what, but just try it in the web browser like Safari or something similar instead of through the YouTube app. So anyway, let's get into it. Just a few reminders about areas, and we've already been doing some of this for quite a long time from chapter 5, and we're just going back into some of this. Remember, the integrals are about area. We've been using integrals for a long time to find area. Remember that area, typically what we refer to loosely as areas below the x-axis, are considered to be negative. And if the problem specifically asks for total area, or specifically quote in quotes area, then you need to make those positive. Sometimes we're talking about, as you remember from the 7.1, there's a distinction between displacement and total distance, and that's analogous to the integral value and the total area problem. So just be careful. And sometimes what that means is you're going to make negative areas positive, just make them positive by doing the opposite, or sometimes you're going to do subtraction of a negative area, and sometimes you do an absolute value. It just depends on what's convenient. Okay. Keep in mind also that as areas or regions are designated, sometimes you might have to find the endpoints for your integrals by finding zeros or intersection points on a graph. And something new that we will add in on this little adventure is sometimes it's easier to work with x equals instead of y equals. Sometimes you have to break up y equals a bunch of times where you can kind of save yourself some work doing x equals. Okay, so with that said, we're going to look at just a quick little note here. I want to remind you about RAM, and when we're doing problems like this, where we're finding an integral, let's say from here to here, just a reminder that RAM, this would be like left RAM, something like this, and you've seen that before. That's not a surprise. And in the notation, as we look at the integral from, let's say this is going from a to b of f of x dx, in the notation, this part is kind of like this. That delta x, I'm going to use that word analogous again, is analogous to a delta x and dx are analogous of each other. They're similar to each other. And then the height is that f of x. Now, the only reason I'm kind of bringing this up right now is because I want to adjust the way we think about finding some of these, and it's really going to be an issue when we're talking about something like this. Let's say this is g of x and this is f of x, and what I want to know is the area from here to here, let's say. Okay, and we can actually treat this like rectangles again. And we're not going to do RAM, but I just want you to picture things this way. Okay, so this is getting to understanding of concept, and I know sometimes we're just so busy trying to, tell me the steps, that we don't understand the concept. But this is going to be more of an issue in the next section. You're going to need to be able to picture things as slices, and so that's why I want you to kind of look at this that way. And so looking at it this way, this distance is actually f of x minus g of x. And this little guy right here is still the change in x, dx. So if I was going to look at the area between those two curves from a to b, I would still be doing an integral from a to b, and the width of my rectangles are dx. And the height of my rectangle is just f of x minus g of x. Okay, I just want to do one more thing similar to that, and that's this. And I know some of you are mad at me because I just scrolled too quickly. Mr. Sanford, I was still drawing that. I'm sorry. Okay, so here's f of x again. And let's say this is g of x this way. Okay, so one of the cool things about looking at it this way is, again, let's start, here's A and here's B. And what, again, I want is I want to know an expression, mathematically, what's the setup for all of that area. Okay, well, if I look at this rectangle here, okay, again, this is the same idea I was just talking about. This height right here is f of x minus g of x. Okay, so the area of that rectangle would be that times dx. Okay, if I pop down to the other end, it looks a little troublesome. Oh yeah, that was a nice straight line. Good job, Mr. Sanford. Thank you. Okay, what's this height? Well, on the other end, I wrote f of x minus g of x. And how would that work when it's negative? Would that actually make for that? This is really extra length down here, isn't it? So keep in mind what's really going to happen is the signs are going to take care of themselves. And the cool thing about this is I don't have to really think that deep about it. So it's still going to be that same area, that same height times the width. This is still dx. And what happens here is it's going to be minus a negative, and because the g of x is below the x-axis, it's minus a negative, and that'll take care of itself. I really don't have to worry about what's happening there. So, some of that area is below, but minus the negative will make it positive and will actually add on area. So it takes care of itself. Okay, so think that through. So moral of the story, when you're finding the area between two curves, you're going to do an integral of basically big minus small dx or dy. In other words, top minus bottom. Or if you're going, so you could actually do work, sometimes what happens is you have some goofy graphs that are sideways, like this. So it could be an integral that's right minus left. And again, it's big minus, and that's dy, big minus small. So, and the idea is the rectangles this time are going sideways. We'll see that in just a minute. So this is actually dy, and this might be f of y, and this might be g of y, and you would subtract those two, f of y minus g of y, etc. Okay, I don't want to spend more time on that. I want to get to some examples. Okay, all right, this example actually is found in our section. It says find the area bounded above by y equals the square root of x. So in other words, the top of the area is this guy, okay, and bounded below by the x-axis and x minus 2. Okay. All right, so we're going to do this exact same problem 3 different ways. And I know some of you find that annoying, but what it does for me is it's a way for me to show you 3 distinct approaches without, and you can kind of see that all 3 of them work. Okay. All right. So what I'm going to do is, the problem with this is I'm finding this area. And this area is dictated by boundaries that are changing. So this up till here, not a problem. From here, not a problem, but there is a problem here, wherever the here is. This here, things change. Okay, so on the left part, I can actually do this just like a regular old integral. I can do an integral from 0 to, well, this is actually at 2, and that's confirmed by what makes that 0. So this is x equals 2. And if this were not such a cute little example, you might have to do some work to find that. So I'm going to do the integral from 0 to 2 of the square root of x dx. And I don't have to worry about a top curve minus a bottom curve so much because the bottom curve, the bottom graph on this is just y equals 0. Now, if you wanted to put it in the form that we were just playing with, the idea is here's this rectangle, okay, and the side of this rectangle would be the square root of x minus 0 times dx. Okay, so if you were going to write that, you'd do from 0 to 2, the square root of x minus 0 dx. Okay, well, the minus 0 isn't really doing anything here. Okay, so it's a non-issue. Okay. Next part of this, though, picks up at 2 and goes until, well, it looks like this point is at 4, 2. Now, just a quick little note here. Is 4, 2 on this graph? Well, 4 minus 2 does in fact equal 2, so that seems to work. But it also has to work here. Is the square root of 4 equal to 2? Yep, it does. Okay, so we're going to go to this x value. Okay, so from 2 to 4. And now again, here's that idea that I have this rectangle, and the height of that rectangle is really the top curve minus the bottom curve. And then that whole thing is times the width of every rectangle. And the concept here is that this thing, this integral symbol, says sum them. It's like an S that got stretched out, and it basically means sum, or in other words, add them up. So that's how we started this back in chapter 5. I know it's been a long time since we did that, but that is where we're at. Okay, so the rest of this now is just turning the crank. It's just doing these integrals. Okay, so I'm gonna rewrite some of this. So from 0 to 2, this is gonna be x to the 1/2. This will be from 2 to 4, again, x to the 1/2, and this is really minus x plus 2 dx. Okay, and we can pretty much just go through term by term. So x to the 3/2 over 3/2 plus x to the 3/2 over 3/2, x squared over 2, 2x. Okay, and we can kind of keep going from here. And I know at this point, you can plug stuff in. So I'm going to hit pause, and I'll just have it appear here, and you can pick it apart as you need to. Okay, that's after the initial substitution of everything. Okay, so this term minus this term was 0. This was 0 also. This term becomes that, and then these things end up canceling out, that and that. And then when all is said and done, we end up with, looks like 22 over 3. Oh, found the mistake. All right, so this was minus a negative, and this will be minus a positive, so that's minus. Okay, so this is actually 16 thirds minus 2, which is 16 thirds minus 6 thirds, which is 10 thirds. All right, there it is. Okay, sign error. Okay, so be careful. All right, so just a quick recap. All we did was we found the integral for the part on the left separate from the part on the right. Okay, and the part on the right, we had to do a top minus bottom, a little subtraction kind of action there, okay? All right, so we're going to take this same exact problem and we're going to do it again, okay? Now, what's going to be different about this is we're going to change it up. What I'm going to do is define both of these as x equals. Now, this is going to feel really weird, okay? So just kind of be patient. I have y equals the square root of x, and what I want is x equals, so I'm going to square both sides. So I have y squared equals x, also known as x equals y squared. And that's this graph, and all we're doing is we're talking about it in terms of x equals instead of y equals. Same idea, okay, I'm going to say y equals x minus 2. I'm going to add 2 to both sides, so x equals y plus 2. Okay, so that's this. Okay, and what we're going to do is treat this problem sideways. I still want the same area. I still want to know this area in between here, but the difference is instead of me taking my rectangles vertical, I'm going to take my rectangles sideways. Okay. Okay. So the whole idea then is this is dy. This guy right here is going to be the red thing minus the blue thing, and these are x values I'm subtracting now. Okay. So how does this help me? Well, the great thing about it is it starts here at y equals 0, and it goes until we get to y equals 2, and it's always about this curve minus this curve. Remember, it's big minus small, so it's going to be right minus left in this case. Okay, so the idea is we're going from A to B. We're saying right minus left dy. Okay, it's big minus small, right minus left. If it was vertical, it'd be top minus bottom. Okay, so here it is. We're saying the integral from y equals 0 to y equals 2, and I know this feels really weird to go this direction, and the width of our little rectangles is dy, and what we're going to say is the right-hand curve, which is y plus 2, minus the left-hand curve, which is y squared. So here's the huge bang for your buck. I don't have two separate integrals for this. It's all one thing, okay? Because there is no third curve coming into this, or third graph like the y equals 0 was on the last one. So I can just go through and do antiderivative and plug and chug right out of the chute. Okay, so this is just going to be, I already did all the setup and everything. So y squared plus 2y minus y cubed over 3. We're going to evaluate that between 0 and 2. Okay, so plug stuff in. So 2 squared plus 2 times 2 minus 2 cubed over 3 minus 0 squared plus 2 times 0. I know many of you are going to just write 0. And that's fine, just as long as you're being careful about things like trig functions or addition or subtraction in there. Okay, so this is 4 plus 4 minus 8/3 minus 0. Okay, that's that whole group there, right? So this is 8 minus 8/3, also known as 24/3 minus 8/3, and that's 16/3. And where did I make the mistake this time? All right, I see it. It happened way back here. This was y squared over 2, over 2, over 2, over 2, over 2. So that means this is really, all right, let me do a little erasing here. Okay, so this is going to be 2 plus 4 minus 8/3, also known as 6. So I'm going to call that 18/3 minus 8/3. Well, sorry about that. That is frustrating. All right, 10/3. Quick little note. We got 10/3 this time. And last time, eventually, we got 10/3. All right, so let me pop back here again just for a second and remind you, the thing that's different about this approach was if we made everything x equals and in terms of y, then that let us not have to break it up into separate integrals. Now, which way's the right way? Yeah, both of them are great. Okay, I want to do the same problem one more time, and this is the one where many of you are going to say, dang, that's how I would have done it the first time. Okay, all right, this to me, this doesn't always work, but I find this awesome, and really, if your goal is to find this area, it doesn't really matter how you do it. What I'm going to do is I'm going to find all of this area. Okay, so all of that area is going to be the integral from 0 to 4 of the square root of x dx. And then the only problem is that I really only want this area, so that means I really need to subtract this bad boy out. Well, the great thing about it is this is made with a line. So this is a triangle. Now, if it was made with a parabola, it's not a triangle. If it was made with a cubic, it's not a triangle. But this really is a triangle. Okay, so I'm going to do that integral minus the triangle. Okay, not delta x, not anything else. It's just going to be minus that triangle. Okay, all right, so antiderivative of x to the 1/2, we've seen this a few times now, x to the 3/2 over 3/2. We're going to integrate that, or evaluate that from 0 to 4. Okay, and then we're going to subtract off, well, the triangle is 1/2 base times height. Well, the base here is 2. The height here, remember this is at 4, 2, is 2 also. So that is really just minus 2. Okay, so I have 2/3 multiplying by the reciprocal, 4 to the 3/2 minus, when I substitute 0 in, that'll just be 0, and then minus 2. Okay, so square root of 4 is 2, 2 to the 3rd is 8. This is 16/3 minus 2, also known as 16/3 minus 6/3. Wow, I'm going to get this right on the first try this time. Woo, I am excited. All right, so don't forget about just using regular area formulas. If you're finding an integral, you can use regular area formulas when it is a shape that you actually know a formula for. Okay, all right, well, that's going to be it for me. I know it's just one example, 3 different ways. The big takeaway from this is that whole top curve minus bottom curve, or right curve minus left curve if everything is x equals something about y. Okay, thanks for watching. This is Sanford Flip Math. Gotta go. Bye.